Okay, today we're going to continue our discussion of stoichiometry, and we're going to learn about what is called limiting and excess reactants. In our last video, I talked a little bit about using that word excess and how the word excess really means extra. And when you think about it, when you think about a chemical reaction that involved at least two or more substances, typically what you'll find is that one of those substances will run out first, and then the other reactant will be you'll have some of that left over. So today, for our objective, we're going to be able to identify these reactants that get used up and are left over, our limiting and excess reactants. And then we're going to be using these limiting reactants to convert to another compound. And then we're going to calculate the amount of excess reactant left over when the reaction is done. So when you think about a chemical reaction, I want you to think, when does a chemical reaction end? For example, when you turn your barbecue on and you let the propane out, C3H8 plus O2, it releases a lot of energy, and you get carbon dioxide and water as your products. How do you make that reaction stop? Well, you close your valve to your barbecue tank, and then the propane runs out. And so in that case, that is the end of our chemical reaction. So when does a chemical reaction end? When one of the reactants is gone. So when one reactant is gone. Okay, what happens to the other reactant that isn't used up? Well, it's just there. I mean, what happens to all that oxygen that's in the air that we're not using? Well, obviously that oxygen is still just there. So it's still there. So if you don't use it all, then you're just going to have some left over. Okay, when you put a strip of magnesium metal into a large quantity of hydrochloric acid, you get a reaction. You get magnesium chloride and hydrogen gas. And yes, we need to balance that. But the reason that this reaction stops is because your strip of magnesium is gone. Well, what about the hydrochloric acid? Well, it's still there. So again, when we talk about reactants, usually there's going to be one reactant that is completely gone, and then that other reactant is left over. So what do we call those reactants? The reactant that runs out, the one that is completely used up, is the limiting reactant. And that makes sense because it limits how far the reaction can go. It keeps the reaction from going. And obviously the excess reactant is the extra one. It's the one that's left over after the reaction is done. So if you look back at a lot of the videos that we've done so far about stoichiometry, you'll see that in most of them I will say something about how, if we have 9 grams of this and excess of this, even though we hadn't discussed it yet, I was kind of leading you into this discussion of limiting and excess reactants. Okay, and I want you to think about this. If you're at a dance club and there's 14 guys there and there's only 9 girls, and every guy can only dance with one girl, which one's going to run out first, the guys or the girls? Well, obviously, you've only got 9 girls, and so the girls could be considered the limiting reactant because they will run out first. Now, sometimes in chemistry, they like to use different words. Reactant, sometimes you'll see this as called a reagent. Sometimes instead of limiting reactants, they call these limiting reagents. A reactant and a reagent are the same thing. So if you see the words limiting reagent, just know that it means the limiting reactant. Okay, so back to this. If there's 9 girls in the club, obviously once 9 girls are dancing with a boy, there will be no more girls. And so there will be 5 boys left over. And so boys, in this case, would be the excess reactant because they are extra. Okay, so how do we use this in chemistry? Just like stoichiometry, this is really nothing new. It's just kind of thinking about it a little bit differently. You write a balanced equation, just like always. Now, here's where you are trying to figure out which one's going to run out first. Now, a lot of times it seems really easy, like if you have something as simple as H2 plus O2 making H2O. If you say, oh, if I got 5 grams of this and I have 3 grams of this, well, obviously the oxygen is going to run out because I only have 3 grams of it. That thought does not work. Okay, as you'll see, it's not necessarily which one's the smaller amount. Okay, if you have 5 grams and 3 grams, I believe it's actually the hydrogen that's going to run out first, and I'll show you how to do that here in just a second. So what you do is you use stoichiometry and you convert from the grams of one reactant to the grams of the other reactant. So again, if we use hydrogen and oxygen as the example, you would take your grams of hydrogen, so again, let's say 5 grams and 3 grams. You would take so step number 2 here, you take your 5 grams of hydrogen and you go 5 grams of H2O, and then you would go 18 grams in 1 mole of water, excuse me, not water, it's H2. Sorry, I messed that all up. Let's see, let's get rid of all that. Let's just try it again here, huh? So if we have 5 grams of H2, there's 2 grams in 1 mole of H2. And then here's our stoichiometry step. From our balanced equation, 2 moles of H2 are going to react with 1 mole of O2. Sorry, that's an M. And then 1 mole of O2 has a mass of 32 grams. So you'll notice that I went from the grams of one reactant. Here's what it says. Use stoichiometry, convert the grams of one reactant to the grams of the other reactant. So we went from grams of hydrogen to grams of oxygen. Okay, now let's do the math there. So 5 divided by 2 divided by 2 again times 32 equals 40 grams of O2 exactly. Okay, now step number 3. So we're done with step number 2. We've converted from grams of one reactant to grams of our other reactant. Step number 3, you're going to compare how much of that reactant you have with how much of that reactant you need. And those are 2 real important words right there. How much you have versus how much you need. This is going to tell you which of the reactant is going to run out first. It's going to tell you which one is the limiting reactant. Now, what this math down here tells us is that if you start with 5 grams of hydrogen, to react with all 5 grams of those, you need, again, there's that important word, you need 40 grams of oxygen. Okay, so that's our need. This number up here, this is how much oxygen you actually have. So if you need 40 grams, but you only have 3 grams, what does that tell you? It tells you that you don't have enough oxygen. It tells you that oxygen is going to run out. These 3 grams of oxygen are going to run out before those 5 grams of hydrogen do. And so in this case, we can now say with a surety that oxygen, that O2, and just because I don't have a lot of space here, is the limiting reactant. And so if oxygen is the limiting reactant, then step number 4, then hydrogen must be the ER, the excess reactant. Okay? Now, that's it. To figure out which reactant is the limiting reactant, that's all that you've got to do. So here's an example of this. First of all, 637.2 grams of NH3 reacts with 1,142 grams of carbon dioxide, producing this compound called urea and water. How much urea will be produced? So number 1, write a balanced equation. So NH3 plus CO2 makes NH2CO plus H2O. All right, this might be a little bit challenging to actually get here. Let's see, we've got one nitrogen on the left. I see two nitrogens on the right with that 2 outside the parentheses. So let's put a 2 there. That makes 6 hydrogens on our left-hand side. There's 4 hydrogens plus 2 more, makes 6 hydrogens. We've got 1 carbon on both sides. 2 oxygens on the left. Here's 1 oxygen and then another oxygen. So actually that was really easy. That is our balanced equation. Now, how do we know that this is a limiting reactant type problem? And the way that you can tell that is because they are giving us the amount of both reactants. Notice that they give us the mass of the ammonia, NH3, and they also give us the mass of the carbon dioxide. And so usually, if it's not a limiting reactant problem, we have to figure out, or we already know, oh, we have excess CO2, then the CO2 is going to run out first. Okay, in this case, when they give you the amounts of both reactants, you know it's going to be a limiting reactant problem because you have to figure out which one's going to run out first, the 637.2 or the 1142. Okay, our next step is to so we have our balanced equation, okay, and now we want to convert the grams of one reactant to the grams of the other reactant. It does not matter which one you use. You can use the 637.2 or the 1142. I'll use the 637.2 grams of NH3, and again, now I'm just going to use stoichiometry to go from NH3 to CO2. So balance, or from the periodic table, NH3 has a mass of 17 grams per mole. And then from my balanced equation, 2 moles of NH3, there's the 2, reacts with 1 mole of CO2. And then 1 mole of CO2 has a mass of 44 grams. So we're going to take 637.2, divide by 17, divide by 2, and then multiply by 44. And I get an answer of 824.6 grams of CO2. Now, again, here's the thinking part. Here's the part where you got to go, okay, what do I need to do here? Here is what this number is telling you, is that to react with all of this NH3, this is how much CO2 you need. Okay, up here in the original problem, this is how much CO2 right here. This is how much CO2 you actually have. Okay, so we need to compare our have with our need. I only need 824.6 grams of CO2, but I actually have 1,142 grams of CO2. I have a lot more than what I need. So therefore, we have extra CO2. So if we have extra, that tells us that CO2 is the excess reactant. Whereas if that's the excess reactant, then NH3 must be the limiting reactant or reagent or whatever they want to call it. Okay? Now that we've identified that, that's an important step. Now we need to figure out, okay, why do we care? Why do we care that NH3 is the limiting reactant? Okay, I'm going to erase this part just so I can use this blank space again. But now I know that NH3 is the limiting reactant. Now, let's look at this question. How much urea is going to be produced? So I do need that balanced equation again, so I'm going to put that back up here. But our question now is, how much of this stuff right here, how much of that urea is going to be produced? Now, let's think about this a little bit. The amount of this that's going to be produced, is it going to depend on how much CO2 we have, or is it going to depend on how much NH3 we have? Go back to that propane example. With propane, how much heat or how much carbon dioxide or how much water is produced, it depends on the propane, because the propane is the one that's going to run out first. The amount of urea, this product over on the right-hand side, the amount that that gets produced depends on which one's going to run out first. And so our whole goal in determining the limiting reactant is so we know when we're actually doing the math that that's the one that we use to figure out how much product we're going to make. We determined that NH3 is the limiting reactant, that once that's gone, the reaction's going to stop. So the amount of urea that's produced depends wholly on the amount of ammonia that we have. So now to answer this question, how much urea will be produced, we use the limiting reactant. We use our 637.2 grams of NH3. Because again, remember, we're going to have extra CO2 left over. We already calculated that. We only needed 800 and something grams, and we have over 1,100 grams of it. And so we're going to have some of that left over no matter what. So now we can just treat this like a regular stoichiometry problem in that we're just going to convert grams of ammonia to grams of urea. So 17 grams in 1 mole of NH3. And then from my balanced equation, 2 moles of NH3 are going to make 1 mole of NH2CO, and then 1 mole of urea. Let's see, 14 times 2 is 28. 28 plus 4 is 32. 32 plus 12 is 44. 44 plus 16 is 60. So there's 60 grams in 1 mole of urea. So now we can say 637.2 divided by 17 divided by 2 times 60 equals, with 4 significant digits, 1,124 grams of that urea compound. Okay, and that's our final answer. So remember, there at the beginning, our whole goal of using these two numbers is to figure out which of those two is going to run out first. And you can't assume that it's always the smaller number. In this example it is, but in many, many cases it's not. You have to do that stoichiometry step where you convert from one reactant to the other reactant and then compare how much you need with how much you have. Okay, another question we might ask with this question is how much of that excess reactant is left over? And I don't remember exactly how much it was, but let's say it was like 864. So let's say we need, we needed 864 grams of it, and we have this 1,142. So the question might be, how much is left over? Well, then we can just take our 1,142 and subtract 864. And again, I might be right, I might not. I can't remember what that number exactly was. But then we get 278 grams. So I might ask you, how much of the excess reactant is left over once the reaction is complete? Well, there you go, 278 grams. Okay, so this is just a page for doing this. Okay, here's another example. Okay, 0.740 grams of ozone. The chemical formula for ozone is O3. It reacts with 0.670 grams of nitrogen monoxide to form molecular oxygen and nitrogen dioxide. How many grams of nitrogen dioxide will be produced? And then here I'm asking you what mass of that excess reactant is left over. So we're going to have ozone reacting with nitrogen monoxide. So ozone plus nitrogen monoxide is NO, producing molecular oxygen. That's oxygen in its as a molecule, so that's O2, and nitrogen dioxide is NO2. Now it looks like we've got 4 oxygens on the left, we've got 4 oxygens on the right. We've got one nitrogen on both sides, so this one is actually already balanced. So we have, and this is what I do a lot of times, is I put the masses underneath each of them just to kind of keep me straight. Okay, and now what we're going to do is we're going to convert from grams of one, from grams of one reactant to grams of the other. So let's take our 0.740 grams of O3. And O3 has a mass, 16 times 3 is 48 grams in 1 mole of O3. And then from my balanced equation, 1 mole of O3 reacts with 1 mole of NO. And then NO has a mass of 14 plus 16 is 30. So now I can just take my 0.740, divide it by 48, times it by 30, and that should be 30 grams there. And I get an answer of 0.463 grams. And again, that's how much NO I need. Okay, how much NO do I actually have? 0.670. So I only need 0.463, but I have 0.670. So this is, again, this is one of those cases, actually, we can answer this question right now. How much of the excess reactant is going to be left over? Well, we're going to use 0.463 of it, but we have actually 0.670. So if we take 0.670 minus 0.463, 0.670 minus 0.463, how much is going to be left over? 0.207 grams. Now, if we had done it the other way, if we had gone 0.67 grams and started up here with that, we would have gotten our grams of O3. Either way, it tells us that we only need 0.463 grams of NO. It's telling us that this is the excess reactant, therefore O3 has to be the limiting reactant. And so now when we answer this question, how many grams of nitrogen monoxide will be produced, we're going to use our limiting reactant. Now you notice this is an example where the bigger number actually is the one that runs out first, not the smaller number. So now let's actually answer the question. How many grams of nitrogen dioxide are going to be produced? So we've got 0.740, right? 0.740 grams of O3. And again, we're using this to answer the question because O3 is the limiting reactant. 48 grams in 1 mole of O3. Balanced equation. We're going to go from moles of O3 to moles of NO2, which in this case, again, is a 1-to-1 ratio. So 1 mole of O3 makes 1 mole of NO2. And then NO2, 1 mole of NO2 has a mass of 14 plus 32 is 46 grams. So I can take 0.740, divide it by 48, and then multiply by 46, and I get an answer of 0.709 grams of NO2. And that is my final answer for this question right here. All right, so that is a good introduction to limiting reactants. Again, if you're having a tough time with this, there is a video at the end of this module that will explain to you. It gives you a couple more examples of limiting reactants. There's the first couple examples are just regular stoichiometry where you already know the excess reactant, but there's at least one, maybe 2 or 3 at the end of that video that involve limiting reactants.